Check it out now, y'all.
nanoHUB-U, online instruction.
Hi, and welcome to Week 4, Lecture 6 of Dynamic Atomic Force Microscopy Methods. We've focused in Week 4 on force reconstruction methods, primarily using frequency modulation AFM. And in the last class in particular, we talked about some key results that have demonstrated the potential of frequency modulated AFM for reconstructing forces, not just long-range van Waals or electrostatic forces, but also short-range chemical forces with extremely high resolution that allow you to actually measure chemical forces between an atom on the tip and an atom on the substrate. Moreover, this capability is now being extended to try and map these interactions in three-dimensional space above a surface, both in surfaces in vacuum, and also in surfaces immersed in liquids these days. So what I wanted to do in this lecture is to just talk a little bit about some key remaining topics on force reconstruction using dynamic AFM methods. These will be somewhat advanced topics, so we can't go into too much details. So this particular lecture is going to be a brief informational overview, more regarding the state of art of some of these advanced concepts. In particular, one of the things I wanted to emphasize that we haven't talked about in the last couple of lectures is the fact that when one uses frequency modulation AFM and approaches the sample, or to start with, when one scans the sample, the dissipation channel is the channel which corresponds to the excitation amplitude required to keep the amplitude constant as you're scanning the sample. You'll recall that when we did the theory of FM-AFM, we talked about the fact that the excitation signal is directly correlated to the tip sample energy dissipation. So going back to the early days of FM-AFM, in this particular case back to 1999, this is again a silicon 111 surface, but there's a terrace on the right, and this is a simultaneous FM-AFM along with STM scanning tunneling microscope. So the topography image is shown on the top, and when for many reasons in this particular problem, in this particular case, when the probe reaches the upper terrace, the features suddenly jumped out with more resolution while the probe was scanning the surface. But the thing I want to draw your attention to is the D and E part of the figure shown on the left. And in D you see the frequency shift, and we notice the frequency shift is more or less constant except the edges of the atoms. But the dissipation signal, which is the damping signal, is shown in C, also shows atomic resolution. And from the early days, it was recognized that one could also start doing spectroscopy, which is approach the sample and try to understand how this dissipation signal changes, and more importantly, what does it tell us about the sample? What physical properties is the dissipation signal related to? So this is called dissipation force spectroscopy, whether it's in the scanning mode, trying to interpret the dissipation maps one gets on a sample, or if one actually approaches a sample, if one is doing it at high resolution, might approach an atom, try to understand what the fundamental dissipation mechanisms are. This is an ongoing area of research, and in many cases, the form or the reason for the dissipation really depends on the specific tip-sample interaction combination that's being used. So one needs to know something already about the likely sources of dissipation when one looks at these images. For example, going back to some of the earliest studies on the subject, work of Denk and Pohl, who actually showed in their case that the dissipation mechanism that they were encountering at a very high resolution was actually related to a non-contact Joule dissipation effect, which is rather interesting because they were oscillating the tip in a non-contact mode of operation in the attractive regime, and yet there was dissipation coming out. So the question that came about was, how is it possible to get dissipation when there is no tip sample contact? In that particular case, the source of the dissipation was attributed to Joule dissipation that arises due to the fact that you have a conducting cantilever. In their case, it was a conducting cantilever, and there's a stray capacitance, and as the tip oscillates, it generates the oscillating capacitance allows the current to flow through and dissipate in some sort of a local resistance. So this mechanism was one of the earlier mechanisms for a conducting tip interacting with the sample. Later on, many different mechanisms have been proposed to understand the contrast mechanisms that develop in dissipation images, especially in high resolution FM-AFM. These includes, for example, the concept of soft modes. The concept of soft modes deals with the notion that when the AFM tip is oscillating on the sample, the sample atoms are not rigidly fixed. In particular, there are many phonons, which are these vibrational modes within the sample. But in particular, one of those modes can have a low enough frequency and can be soft enough that it actually responds to the oscillating tip, and the other modes don't. In which case, when a tip is oscillating near a sample, the soft mode can start moving also, and can very high short time scales snap into the oscillating tip or pull away from it. You can have situations where there are multiple states of these soft modes, that they're attached to the tips or off from it. There can be ratcheting and all kinds of interesting transitions that happen in very small distances between the tip and the sample. So this is known to be one of the dissipation mechanisms that's relevant when the right tip sample combination is used. Many other mechanisms have been proposed as listed here and have been verified, but this remains very much an ongoing area of research. And I just wanted to bring it up because we haven't really talked about dissipation spectroscopy in FM-AFM in this class so far, but it is an important subject, an ongoing area of research, and again, we hope to see more results coming out in this area in the future. So I want to turn my attention to tapping mode AFM again. Now, in this whole week, we've been talking of how dynamic AFM methods can be used for reconstructing forces, and all along we've been talking about the use of frequency-modulated AFM, which tracks frequency shifts and excitation or dissipation as a function of Z. The question that comes up is, well, if frequency-modulated AFM can be used for reconstructing forces, why not tapping mode or amplitude modulated AFM? Now, you may recall that in tapping mode AFM, the observables are different. We drive the cantilever probe with resonance, approach the sample, and as I've shown in this simple Veda simulation, the parameters of which are shown in the appendix, but you see the amplitude of this oscillator plotted as a function of Z, as one is approaching a polymeric sample in this case. And on the right-hand side, we've got the phase. So our observables in this case are amplitude versus Z and phase versus Z. And the question is, can we use amplitude versus Z and phi versus Z curves on a surface to reconstruct the F versus D, just like we did in the case of frequency-modulated AFM? Now, there are obviously going to be some compounding factors, one of which is the fact that, fortunately, in FM-AFM, the frequency shift, which is a separate observable, is only related to the conservative interaction forces. In the case of both these variables, observables in tapping mode AFM, amplitude and phase, as we've talked, both are actually influenced by the conservative as well as the dissipative interactions. So that's going to be one of the challenges as we look ahead. But let's go back to a result that we got some time ago that suggested that while the amplitude and phase are the two direct observables in tapping mode AFM as you approach the sample, that these two observables are related to what I call intermediate observables, which would be the virial and energy dissipation, which the relationships between the amplitude and phase and the virial and dissipation are shown in equations 1 and 2. We've discussed this earlier in the class. These expressions are for the special case when the drive frequency omega is exactly equal to the natural frequency of the oscillating probe. A far is the oscillating amplitude of the cantilever far from a substrate. Some people call it free amplitude. Sometimes it's called unconstrained amplitude. But the key thing is that one is able to, using these expressions, convert the amplitude and phase versus Z relationship that I showed you on the previous slide into virial versus Z and energy dissipation versus Z, as shown on the right here. So we have these intermediate observables, dissipation and virial versus Z, and the question is, how can we use this information to back out the tip sample interaction forces as a function of D? In equations 3 and 4, I've shown you the relationship between the amplitude and the phase. And as I mentioned to you in the previous slide, you can see that the amplitude itself and the amplitude reduction specifically is connected to both the virial and the dissipation. And the phase also has both the virial and the dissipation involved in them. So one cannot expect to use the amplitude versus Z alone to get the conservative interactions. And one cannot expect to use the phase versus Z to get the conservative interactions. Both have to be coupled, and we have to use both of them to untangle the conservative and dissipative interactions. If we do come up with a scheme for doing so when one approaches the sample in the tapping mode. Again, this is different from frequency modulated AFM, where the frequency shift versus Z alone can be used to back out conservative interaction force as a function of distance. All right, so just like we did in the case of FM-AFM, we're going to look at this in different limiting cases. The first limiting case is going to be when the oscillation amplitude A is much smaller than Z or D star, which is the tip sample equilibrium distance. Now, we had shown that in this limit, the virial simplifies very easily to this expression, which is negative KTS A squared over 2, where KTS happens to be the gradient, the negative of the gradient of the interaction force, conservative interaction force, relative to the gap D. Another result, which was discussed in the appendix of the week 2 lectures, was that in this limit, the energy dissipation is also given by CTS, which is the local velocity proportional damping of the tip sample interaction times omega squared times A squared over 2. So all we need to do then is to take these approximations for the virial and the energy dissipation, which are valid in the infinitesimal amplitude limit, and apply it to the equations I described earlier. We get the following equations, from which it's easy to separate KTS and CTS, as shown in equation 4, which allows us a very nice and elegant way to convert the amplitude versus Z and phase versus Z into local gradient as a function of D, and local dissipation or viscous dissipation coefficient CTS as a function of D, or as a function of Z in this case. The key thing it requires us to do is to measure amplitude and phase as a function of Z. We plug those observables into the right-hand side, and we get estimates of the force gradient and the dissipation as a function of the tip sample gap. However, as simple as this relationship is, the result applies only in the limiting case when the oscillation amplitudes are much smaller than the gaps. This is usually or very rarely encountered in practice. Perhaps it could be used in situations when one is looking at long-range electrostatic forces and oscillating the cantilever with small amplitudes, or one is dealing with very soft materials and oscillating with very small oscillation amplitude. So really this approximation tends to be valid in the case of long attractive force gradients, long-range attractive force gradients, or when dealing with very long-range repulsive interaction gradients, when one deals with extremely soft materials where the Young's modulus might be less than 10 megapascal or less than a megapascal or so. In those cases, this assumption might actually be reasonable and valid. Now, the second caveat in the use of this formula is that this whole description of virial and dissipation and how it relates to interaction forces is strictly valid for the case of, or strictly speaking is valid for the case of directly excited cantilevers, which are like the magnetic excitation or thermomechanical excitation and so on. It can, of course, also be used in vacuum or ambient settings, because in those settings, the base motion is very small compared to tip motion. So at the end of the day, using this kind of relationships would also be valid for base excited AFM, but so long as the base motion is very small and you're in ambient conditions or in vacuum. However, using these equations in liquids, for example, where the Q factors become very small, the base motion becomes very large, as we have talked about in the past, these expressions are not going to be, these reconstruction expressions need to be changed to account for the larger base motion, and also for the fact that the observable is not the absolute tip motion like we have talked about in the past. So these are the limitations of the small amplitude analysis, which brings us to the natural question as to, when we step back and look at the fact that we derived a very nice relationship between frequency shift, which is delta omega divided by omega naught, we showed that it's actually directly related to the virial, VTS divided by Ka squared with a negative sign. So the question is, if we can take the frequency shift versus Z data and convert it into interaction forces, why can we not take virial as a function of Z and convert it using the same approximations into interaction force versus D? This has been the underlying goal of a group of researchers who have been trying to push the concept of force spectroscopy within the realm of amplitude modulated AFM. And the first attempt at doing so within the theoretical context that I've talked about was by Henry Kulcher's group. And what they basically did is they used the large amplitude approximation. Recall that when we had our expressions for frequency shift, they were related to the tip-sample interaction forces, and there was an approximation that allowed us to invert the relationship, and the approximation was under conditions where the oscillation amplitude was large compared to the decay length of the tip-sample interaction forces, which allowed the inversion of the integral and easy conversion of frequency shift into interaction forces. What was demonstrated in this particular paper is that because the frequency shift is related to the virial, one can pretty much use similar approximations and apply it in the context of AM-AFM. The only challenge that comes up in this case is that unlike an FM-AFM and AM-AFM, we have this problem called the jump from attractive to repulsive regime of imaging, as we have talked about. In FM, we don't tend to have that. In AM, that you can reach certain Z values where there's a sudden change in the tip, which is oscillating from one oscillation state, so it goes into another oscillation state, which makes the reconstruction of forces quite difficult, especially while using the large amplitude approximation. Nonetheless, this method is there and has been demonstrated, and as you can see from the data out here, this is an example of an oscillating tip approaching a silicon surface in ambient conditions. You see the amplitude and phase data. And by the way, what's plotted here is actually the phase lead, not the phase lag, versus Z. And this information can be converted using this large amplitude theory into tip-sample interaction force as a function of D. What I want to emphasize here is that because of the challenge involved in the conditions under which you transition from attractive to repulsive regime, there is a fundamental problem that arises in using this reconstruction method when one is trying to reconstruct the interaction forces and once the tip has gone into the repulsive regime of oscillation, and that's because of the fact that when the tip is in the attractive regime of oscillation, it approaches a certain minimum distance, and as you approach the Z a little further and transitions to the repulsive regime, the minimum approach distance of the tip changes suddenly from being a certain distance from the surface to really impinging on the surface. That discontinuity creates numerical problems which require us to stick to the reconstruction in only the attractive regime when one is dealing with these kind of transitions or jumps. On the other hand, if you change the operating conditions to be always in the attractive regime, then you can apply it for the entire region, or you can change the operating conditions, you're always in the repulsive regime, then you can consistently apply this formulation. But what I'd like to point out is one is able to reconstruct the conservative interaction force as a function of tip sample gap in the attractive regime of oscillation very comfortably and nicely. There are other approaches that try to circumvent some of the challenges that I just described. The first was developed by Jane Lee, who basically took the expressions for the virial and dissipation, and what they effectively did was they wrote down the virial and dissipation in terms of Bessel's functions or expansions using Bessel's basis functions, whose coefficients would then need to be backed out from the measured data. They demonstrated a theoretical approach for doing so, and demonstrated that in principle, as you increase the number of terms, you can actually back out the answers pretty well. Another way to approach this is not to write the virial and dissipation in terms of their approximations, but rather approximate the tip sample interaction force itself. And in this case, there was work done at Purdue. The idea was to write the tip sample interaction forces in terms of Chebyshev polynomials, whose coefficients have to be determined. And these forms were then, these expansions of the interaction forces were then taken into computing the virial and dissipation. And then what one would have to do then is, from the experimentally measured virial versus z curves, one would have to back out what should be the coefficients of the Chebyshev polynomials that best fit the measured data. Now, this requires the inversion of a matrix. In some sense, it's not very much unlike what has been proposed in the frequency modulation area, the matrix method. It is a little time-consuming, and it requires the use of several Chebyshev polynomials, but the results experimentally are nonetheless very good. What is demonstrated on the right, for example, is on the top is the amplitude versus and phase versus z on top of polymer, a PVC sample in this case. And one goes through the amplitude and phase data, converts it into nearest approach distance, or one also determines the nearest approach distance versus z data, which is shown in the second row, and converts it into these observables into frequency shift, which, as I mentioned to you, is related to the virial. And then one then backs out what the coefficients of the Chebyshev polynomials need to be in order to match the observed frequency shift versus z. And the reconstructed force is shown on the bottom right. And it actually does quite well, and shows that one needs several terms to be able to approximate it pretty well. On the bottom left is shown another example. This is on a much lower elasticity sample. This is a low-density polyethylene sample, but this is the interaction force that's been reconstructed with different initial amplitudes of oscillation, suggesting that in spite of the different initial oscillation amplitudes, the reconstructed force is basically the same. So this is another approach that has been considered to deal with this situation. Yet another approach was the one proposed by Allard-Catan and Osterkamp's group, and they went back to the attempt that Hendrik Hulscher suggested, which is to use the large amplitude approximation. But in this case, they came up with the idea that, if we can use the Sater-Jarvis formula for arbitrary amplitudes to convert frequency shifts into forces, why can't we borrow that approximation of the inversion that was done in the Sater-Jarvis method and apply it to AM-AFM? Because after all, we're also measuring virials versus distance, which is related to frequency shift versus distance in this case. And So that was implemented and is again one of the good techniques around, promising techniques for doing reconstruction in AM-AFM. What's shown at the bottom is experimental data. They acquired an HOPG. The amplitude versus distance, phase versus distance graphs are shown. Again, this is phase lead versus distance. And the interaction force can actually be reconstructed using this method. In this case, they have tried to use this reconstruction method to determine the electrostatic forces, which are mainly attractive forces, and they're able to show that they're getting very good results regardless of the oscillation amplitude that was used. However, there is a challenge that is mentioned in this paper, which is the fact that the Sater-Jarvis formula, specifically the interpolation term in the middle of the integral, does require, or its accuracy is certified in the situation where the amplitude of the oscillation is kept constant as you approach the sample, strictly speaking. So when one is using that formula in the situation of tapping mode AFM, where the amplitude changes as you approach the sample, there is a question that comes up about how uniformly accurate is that approximation. But based on the results that this group has shown, we may not have a mathematically rigorous way of showing that the approximation is a good one, but nonetheless the results do show promise in that we are able to get pretty good reconstruction of interaction forces using this method. So with that, I'd like to end this week 4 of the course, and starting in the next week, we'll transition to talking about interesting applications to measuring electrical forces, electrostatic forces, magnetic forces, and to do AFM, dynamic AFM in liquids. Thank you.